So while this implementation finishes up, you should see right up here that it says mapping and routing. What it was doing is actually mapping and routing all of the inputs and outputs that you created to their appropriate location that we specified. So without a correct UCF, implementation would have never gave you this green check mark. Alright, so the next step you would want to do after you have successfully written your module, synthesized it, and implemented design, the next step you would want to do is create a test bench for it. So to create a test bench, you would move from implementation to simulation. You would right click here in the hierarchy, hit new source. You want to create a Verilog test fixture, give it a name, test bench for 7seg, and you want to associate it with the module that you want to simulate. So associated with that one, hit next, hit finish, and it'll create this template for you. So in this template you'll see that it has the standard header, standard time scale, and the title, module name, inputs. So what you see different from our module that we wrote in the test bench is that all of our inputs and outputs, well, all of our inputs that we have in our module are now registers in the test bench, and all of our outputs from our module, all of our outputs are now wires. So what we're doing in this test bench is actually instantiating the module we created. So here is the title of the module we created. It is the unit under test, UUT, and we are inputting all the registers to your inputs and taking all of the outputs to be wires. You keep scrolling down, you'll see that we can actually manipulate the registers. So the inputs, we can manipulate them to be whatever we want, and therefore we can evaluate the outputs and see what the module itself is doing. Alright, so besides this, all you would have to add is some stimulus. So we want to change its inputs, Control C. It tells you to add stimulus here, so Control V. Here you just change the inputs and add delays, so that way we can evaluate to see what happens under those inputs conditions. So this pound 100, as it says here, it waits for 100 nanoseconds. So it's just a delay, but it can only be used in test benches. In actual modules, the pound 100 does not work the way it's supposed to, the way you would expect it to. So the only last thing you would have to do is create a clock to represent the oscillator on the BASYS board. So to do that, all you would have to do is add a always begin, and you add a delay of 5, and then you say that clock equals not clock. Put a semicolon there and put an end to go with that begin, and this block just creates the clock and it oscillates it every 5 nanoseconds. Alright, so this is pretty much all you need for your test bench. The next thing you should do is hit save. You'll see that it shows a test bench with the tutorial module that we created instantiated within it. And you see, if you highlight test bench, you come down here, check for syntax. Once syntax is good, you can go ahead and simulate it. So by double clicking this, we can go ahead and simulate. And what we see is that our outputs are not displaying what they should be. So what we'd want to do at this time is go back to our Verilog module and see why our outputs, the cathodes and the anodes, are not doing what they're supposed to do. We do see that this clock does oscillate. It should be resets not pressed, and our inputs are what we made them to be. So at this time you would close this and you would go back to your module, your tutorial module, tutorial 7 segment 2 module here, and you would evaluate to see why it is not providing the correct outputs as shown here. So here, whatever SSEG was, which is whatever the input is at that time, so this is probably not happening because the count is never triggering these to switch positions. Anyway, you would then play with this, or you would evaluate this module to see why the test bench is not doing what it's supposed to in simulation. However, I have already created this module several times, and I know that it actually works. So it's just something in the test bench that we have not entered correctly. Let's see, that's 2. Back to simulation. Simulate behavioral model. Yes. And we still don't have the appropriate signals where they need to be. So just for time, I'm going to move on past the simulation. And then the next step would be to generate a program file and program your hardware. So I'm going to double click on generate program file. Again, I had to go back to implementation so that I can get these options. So I clicked on implementation, made sure that the top module was highlighted, and double clicked on generate program file. It generated a green check mark which says that it is now complete. To find the location where it saved the bit file, it always saves it in the same location as the .v file that we just created here, the module. So for me, you will see that it is under desktop, project lab 1, Verilog, tutorial SSEG2. So I can open up my adept program and turn on my BASYS board. Initialize chain, it's connected, and then verifying that my PROM, or my mode selector up here, the little blue jumper, is on the ROM setting and not on the PC setting. So once I verify that it's on the ROM setting, go back to our adept folder, go to the PROM option here, hit browse, and then we can go to Project Lab 1, Verilog, tutorial SSEG2, and here's the bit file that we want to select. As you see, it was generated a minute ago when I double clicked on generate program file. So this is the correct one. I can double click on that and tell it to program. As always, it'll tell you it's erasing the device, and then it gives you status for programming. Programming is successful, and now we can show you the BASYS board. Alright, so here we have the BASYS2 board. It's been programmed. I'm going to go through the programming steps one more time just so you can see what happens on the BASYS board. Here it's being powered by these two jumpers, which seem to be loose and keep coming off. But if I reprogram, you will see that the red LED keeps blinking until it's finished, and then it stops. Once it stops, it tells you that now you can turn it off and turn it back on, and the program has been successfully loaded, so that these 4 switches represent this digit and these 4 digits represent this digit. So as you see, only this switch is on, so therefore it's showing a 1. If I wanted to show a 2, I hit that. A 3, hit that. 4, 5, 6, and so forth, so on. Same thing with this other input. So we have a 4-bit input that controls this digit. And again, 2, 3, 4, 5, 6, and so on. One thing we do see though is a little bit of ghosting effect. So if we change this digit to an 8, you see that middle segment on that digit is accidentally being lit up. So that is called ghosting. It is created because there is no turning off in between digits. So in more sophisticated modules, you would want to pause in between switching digits, so that way you do not create that ghosting effect. But as you see, even if the 8 is on the first digit, it still creates that ghosting effect to the 3rd digit. So as you see, we can go ahead and unplug it from the USB. We can go ahead and power it off again, power it back on, just to show you that the program is loaded onto the BASYS board, onto the memory. And again, you can power it off and on as many times, and the same program will still be loaded that we programmed onto the board. Alright, so that is it of creating a module to control the 7-segment display. More sophisticated modules can be adapted from this basic 7-segment multiplexing module. Alright, well, hopefully you learned something, and I'll see you at the next videos.